In this video, we're going to talk about flow integrals and circulation. Now, what I want to begin with is contrasting two different vector fields. The one on the left, who's given by the equation xi hat plus yj hat, has the property that everything is dispersing from the origin. That is, at any point, the direction of the vector field is directly away from the origin. Whereas the one on the right here, which is given by minus yi hat plus xj hat, is a spin field. It has this behavior where everything appears to be rotating counterclockwise. Now, so far in vector calculus, we've seen that vector fields can have a bunch of different physical interpretations. For example, we've seen that it could represent a force field like that comes from gravity. But in this video, we're going to imagine these vector fields represent velocity fields. For example, in some turbulent water system or turbulent wind system, you have a point, and then the vector tells you the magnitude and the direction that either the wind or the water is flowing at that particular spot. And thinking of these vector fields as velocity fields is going to really build some physical intuition for the concepts we're going to introduce in this video of flow and circulation. So now I want to imagine you take some path that goes through this vector field. It goes around in a counterclockwise circle. And I'm going to do the same thing for the other one. In other words, I have this same basic path, but in two different fields. Now, there is a difference between these two cases. For the spin field, the path sort of aligns with the vectors. You could imagine, for example, if you had a spinning body of water and you were just paddling your canoe in it, then you can imagine you wouldn't have to paddle your canoe at all because the velocities of the water was going around in a circle and the path you wanted to take was going around in a circle. You would just thus not do anything and the water would move you around in your circle. Whereas if you're in this field, that's sort of more like a source, like I could imagine, for example, a water fountain in the middle and then everything disperses away. Well, it would take a lot of work. You have to do a lot of paddling to actually be able to travel in a circle because you'd always be going orthogonal to the velocity field of the water that you were paddling in. So I want to capture this concept. I want to figure out some notion that I'm going to call flow, and flow is going to represent the degree to which my path is aligned with the vector field. Okay, so here's our formal definition. It says, if you have a velocity field F and a smooth curve C, then the flow integral is just the line integral of f dot t ds. Now, what you might observe is that the formula I've given here is exactly the same formula. There's nothing new about it as the formula that I gave when we talked about work done by a field on some particle moving along a path. So the actual line integral, the mathematics of it, is the same. What's changed here is the physical interpretation. Again, if I look at the integrand, what I have when I look at the f dot t is I'm saying, well, t is the tangential vector to the curve. I'm saying I want to add up the contributions of the field in that tangential direction. Now, as we've seen before when we looked at, say, work, this formula is a great definition, but if we're given an explicit r of t, a parameterization for the path, we need a way to compute it. So exactly as we've seen before, we get the parameterized version of this formula. So it's the integral from a up to b, if your path is parameterized where t is going between a and b, of f of r of t dotted with r prime dt. And so thus, if you know your field and you know your r, you can just plug it into this formula to compute it. We've also seen in the video on line integrals with respect to x is that we can rewrite this in a new shorthand. We can just call it the integral of m dx plus the integral of n dy. I often like remembering this third version of it. It's just sort of a shorthand that I think is really simple. I just plug in the m and the n, and then I have to remember the dx and the dy are always going to be g prime of t dt and h prime of t dt, respectively. So regardless of whether you use the second or the third equation here, these are what you use to actually compute it. Final bit of terminology is this is just a general curve, but if the curve is closed, and what I mean by closed is a curve that ends up exactly where it started. So for example, the standard curve is just the circle going around with t between 0 and 2 pi. It's a closed curve because the value at t equal to 2 pi, the end, is the same as the value at t equal to 0, the beginning. Anyways, when your curve is closed, we give it just a new word. The flow integral is just called the circulation. And to indicate that, we add a new symbol. So it's the exact same formula, except our integral sign has this little circle inside of it. And that just indicates that it's a closed curve. And indeed, some of the concepts that we're going to see in this course are going to be dependent and only work when it's a closed curve. And so it's important to have this way to distinguish them. So when it's closed, you put the little circle on the integral. Other than that, it's the same. And we give it the new word, the circulation. So what is the circulation? The circulation is the total flow when you go around one loop of your closed curve. All right, so back to our two different fields. What should we guess the circulation is in these two cases? Well, for this dispersion field where everything's leaving from the origin, there is no spot at which the vector field is tangential to the curve. Anywhere around this circle for this field, it's the case that the vector field is actually completely normal to the curve. So if you're thinking about what the flow does, flow is a measure of the degree to which you go along with the vector field. It's the degree to which if you're in a canoe, you don't have to paddle because you're just flowing along the river with the velocity flow of the river. Well, in this case, since everything's normal, that never happens, and so there is no flow or no circulation around the entire curve. In contrast with this case, at every point, the velocity field is tangential to the curve. So we're going to have a lot of flow. The exact number we're going to have to figure out. So I'm actually going to ask you to pause and go and compute what is the circulation in each of these two cases. The one I suggested was 0, but prove that to me, and then the other is going to be some positive number. What number is that going to be? So I'll give you a moment to go and compute that, but if you just are here to watch the show, then, well, let me walk through the first of them quickly. I'm going to begin with the xi hat plus yj hat field, the one where everything's dispersing from the origin. I'm going to first, as I always need to do, parameterize my curve. This was the standard circle. So my standard parameterization for the circle is cos of t in the I hat, sine of t in the j hat, and t between 0 and 2 pi. Don't forget, you always have to take the limits of your parameterization. The formula we had computed was that flow was the integral of m dx plus the integral of n dy. So that's my definition, but now I need to plug the values in. So m here is, well, if I look at my field, was just x, and x is cos t. So the m is cos t. dx I can replace with g prime dt. If g is cos of t, then the g prime is minus sine of t dt. And then likewise for the integral of n dy, I'm going to have sine of t cos of t. And notice these are exactly the same, except for a difference of sign, and so they add up to 0. So indeed, the field that we anticipated would have 0 flow, indeed has 0 flow. And then for the second one, you can walk through it yourself. I've changed the field here. It slightly changes the m and the n, and gives the value of 2 pi. So where am I at? Well, I have my two different fields. For the left field, where the field was normal to the curve at every spot, we managed to compute out that the flow, or since it's a closed curve, perhaps I should say circulation, was just 0. But for the spin field, where indeed we had these tangential field components to the curve at every spot, it actually added up to 2 pi.